Welcome to Introduction to Optimization Tutorial 9, Augmented Lagrangian Penalty Functions and the Minimax Theorem. A quick reminder on the Lagrangian you have seen in the previous tutorial. So we have the following optimization problem. We want to minimize f of x given that g of x is smaller or equal to 0 and h of x is 0. So we will define the function L of x, lambda, and mu, which is f of x plus lambda transpose g of x plus mu transpose h of x. We know that if the KKT conditions hold for some point x star, lambda star, and mu star, then the point x star is the optimal point on the function f that hold the condition g of x is smaller or equal to 0 and h of x is equal to 0. The KKT conditions. So a point x star, lambda star will hold the KKT conditions if and only if the gradient in relation to x of the Lagrangian is equal to 0 at the point. For every inequality constraint g at x star is smaller or equal to 0, every equality constraint h in point x star is equal to 0, lambda star is a vector and g is a matrix function that holds all the constraints but could be decomposed to sigma lambda I gi x. That is meaning that we squeeze the inequality and equality constraint into one variable and one matrix. And so lambda I is equal to 0 for non-active constraint, meaning they don't affect the solution, and lambda I is larger or equal to 0 for active constraints. We know that the sum of lambda I gi of x is equal to 0 and could be written as lambda transpose g of x is equal to 0. Note in our case that the lambda variable contains all the variables for all the constraints. We denote lambda as lambda mu, and g contains all the constraints functions. Penalty functions are a powerful tool for numerically solving constraint optimization problems. So when we're given a constraint optimization problem, such as minimize f of x given that g of x is smaller or equal to 0, one way to solve it is to penalize solutions that do not satisfy the criteria g of x smaller or equal to 0. This way we'll define a new function. Big f of x is equal to f of x plus phi of g of x, while phi is a penalty function. Penalty function for inequality constraint would be 0 for values below or equal to 0 and would be a very big number for numbers that are larger. If you want a penalty function for an equality constraint, we need a function that would be 0 only at 0 and would be very large numbers in any other location. The ideal penalty function would be phi of x is equal to 0 when x is smaller or equal to 0 and infinity when x is larger. Some examples of penalty functions are phi of t is equal to e raised to the power of t minus 1, or phi of t is equal to this function. The penalty function needs to hold the condition that it is convex, monotonous, and smooth, and the limit when t reaches infinity of phi prime t is infinity as well, and lim of t when t approaches minus infinity of phi prime is 0. We want that phi of 0 is 0 and phi prime of 0 is 1. The penalty function algorithm. So one could simply use big f of x as defined before, but this method does not promise always the optimal solution or efficient convergence, because we can have a point that is not in the feasible set, but the penalty is not big enough, so our min point would be in an infeasible location. So we have the penalty aggregate algorithm. So for a given penalty function phi, we will define phi p of t as 1 over p of phi pt. By this, as p approaches infinity, phi p of t approaches the ideal penalty function, meaning that for any infeasible point, the penalty would be much larger than the reward the algorithm will get by going to this point. So we will define big fp of x as f of x plus sum over I of phi p of gi of x. So phi p is as we've defined before, and gi of x is each of the constraints we want to hold. Penalty aggregate algorithm. So we will start with phi 0 as the penalty function and x 0 as a starting point. xk plus 1 is being achieved by minimizing fpk over x. To optimize fpk over x, we will use xk as a starting point, while xk is the optimal value that's been achieved in the previous iteration. pk plus 1 is equal to alpha multiplied by pk, for some alpha that is a hyperparameter of the algorithm. Alpha needs to be bigger than 1, so p would approach the ideal penalty function. Usually we'll stop when p reaches around 10 raised to the power of 5, 10 raised to the power of 6, or another stopping criteria, and we would not use big F over 10 to the 6 straight away, because then in the infeasible areas the gradient will explode and cause errors or slow convergence. This way, we ease into the right solution by penalizing only a little bit for every wrong solution, and always moving a little bit closer to the right solution. The derivative using the augmented Lagrangian. Sometimes, to encourage the solution to go to the feasible area, we want to increase the derivative of the penalty function at location 0. We will use phi mu p as mu multiplied by phi p. Because for every phi p, we know that phi prime p at location 0 is 1, then phi prime over mu p at location 0 is equal to mu. And so we will define the augmented Lagrangian as L of x mu as fx plus sigma phi p mu I over gix. And the optimization algorithm will be x at iteration k plus 1 is equal to arg minimum over x of Lx mu k. Mu I in iteration k plus 1 is phi prime of p mu ik in gix. What does that mean? It means that for every constraint, we want the derivative it had in the location x at the previous iteration, that this would be the new derivative at location 0 for the same penalty. That meaning that if the algorithm wants to keep the same derivatives over the penalty of gi, it needs to go at least to location 0. pk plus 1 is the minimum between alpha pk and max p. This way we constrict p to not get too high. And this way each penalty will need to zero out at the next iteration to keep the same derivative as in the previous iteration. To prevent the penalty from zeroing out when we are in feasible areas, we have another constraint that mu I in iteration k plus 1 divided by mu I in iteration k is smaller or equal to 3 and larger or equal to 1 over 3. This means it can be only big or smaller than the previous iteration only 3 times. The minimax theorem. For any given function f, for every z, max omega of fz omega is larger or equal to minimizing over z of fz omega, meaning that any point of this function of z is larger or equal to any point of this function of omega. The scalar max fz omega for any given z is larger or equal to any value of the function minimizing over z fz omega for any value of omega. We know that max omega of z omega is larger or equal than any point, and so also if we take the maximum over omega over min z of fz omega, we would get a larger value. This is true for any value, so this is also true for the maximum value. And so also if we pick the minimal one over this side, we get that minimizing over z and then maximizing over omega is larger or equal than maximizing over omega and then minimizing over z of fz omega. And so we got that for every function f of z and omega, minimizing over z and maximizing over omega is larger or equal than maximizing over omega and minimizing over z. This means that if we change the order of minimization and maximization, if we first maximize and then minimize, we will always get a larger or equal value than if we first minimize and then maximize. But when do we get full equality? The saddle point theorem. So if exists a saddle point z star omega star, the definition of a saddle point is for every z in omega, fz omega is smaller or equal than fz star omega, And for every z omega, fz omega is larger or equal than fz omega star. Then, if for a function exists a saddle point, we know that minimizing over z and then maximizing over omega of fz omega is equal to maximizing over omega and then minimizing over z of fz omega. The proof of the saddle point theorem. So we know that this part is correct because it's always correct. That is the minimax theorem for every function. And we know that min over z of max over omega of fz omega is smaller or equal than fz star omega star, which is equal to fz star omega star. Because we have picked the omega to be max over omega of z omega, and so by the definition of the saddle point, this omega has to be omega star. Fz star omega star is equal to the minimizing over z of fz omega star. By the definition of the saddle point, we need that by the definition of the saddle point, the z would be the minimal one and the omega would be the maximal one. And so minimizing over z of fz omega star is smaller or equal to maximizing over omega minimizing over z of fz omega. And we got in total that maximizing over omega and then minimizing over z is smaller or equal than the same omega and using z star as the z from the saddle point. That is equal to the saddle point itself. And that is equal to minimizing over z using the omega from the saddle point. That is the same definition. As that is smaller or equal than minimizing over z, maximizing over omega. And we also got that the other side, that maximizing over omega and minimizing over z is smaller or equal than minimizing over z and then maximizing over omega. So that means that min max is equal max min. As we have seen in the lecture, we have a saddle point when the KKT conditions apply, and then x star lambda star is the saddle point of the Lagrangian. This part is full of notations and largers and equals and using the definition, so I suggest you pause the video and wonder and explain to yourself why this is true. So we have seen the minimax theorem, but what does it help us? So if we want to find the optimal point for a constraint optimization problem, we know that if we take the maximum over lambda of the Lagrangian, we would get f of x if x is feasible, because then the constraint would be larger or equal, smaller or equal to 0, and infinity if x is not feasible, because then we have some constraint that is larger than 0, and we can take lambda that would explode it to infinity. We note that lambda has to be larger or equal to 0 using the KKT conditions. And so our desired point is minimizing over x, maximizing over lambda of Lx lambda. Using the minimax theorem, we know that the KKT condition apply when the function f and the constraints are all convex. And then we would know that maximizing over lambda and minimizing over x is equal to minimizing over x, maximizing over lambda. We will define mu of x as maximizing over lambda of Lx lambda to be the dual function. So if we can find this function, mu of x, we use regular minimization by taking the gradient, equating it to 0, or gradient descent, or any other algorithm, and we could solve the constraint optimization problem. Let's consider the following question. We want to minimize f of x being x transpose a0x plus 2b0 transpose x, given that gi of x for every I that is given as follows would be smaller or equal to 0. We know that a0 to am are n by n symmetric matrices, and b0 till bn is in Rn. Ci, c1 until cm is in R, and we suppose that x star satisfies the following conditions. There are lambda 1 until lambda m that is larger or equal to 0, such that a0 plus the sum from 1 to m over lambda I ai multiplied by x star plus b0 plus the sum over lambda I bi is equal to 0. Also, for every I, lambda I multiplied by x star transpose ai x star plus 2bi transpose x star plus ci is equal to 0 for every I, and also x star transpose ai x star plus 2bi transpose x star plus ci is smaller or equal to 0. We are also given that a0 plus the sum over lambda I ai is a positive semi-definite matrix. Let's prove that x star is an optimal solution for the problem. I encourage you to try to prove it yourselves and view the solution only after. You can look at these conditions and they remind us of the KKT conditions of optimal solution for constrained optimization problem. We will define the Lagrangian for any given lambda as Lx of lambda being the definition of f plus the sum over lambda I x transpose aix plus 2bi transpose x plus ci, which is the gi constraint. So we know that for any feasible solution x, this condition holds. This condition is, this is the Lagrangian, this is the definition of f, and those are the constraints. And we know that if x is feasible, all the constraints are smaller or equal to 0. So that is smaller or equal than this expression, which is the definition of. Now let's rewrite the Lagrangian as follows. Let's take x transpose out, and we would get x transpose multiplied by a0 plus sum over I from 1 to m lambda I aix plus 2 b0 sum from 1 to m lambda I bi transpose multiplied by x plus the sum from 1 to m over ci. So we can see that this is a quadratic function, and the Hessian is this matrix. As we were given over here, we know that this matrix is positive semi-definite. So, we know that because this matrix, which is the Hessian of the Lagrangian for any given x, is positive semi-definite, the Lagrangian is convex, meaning that the KKT conditions apply here. Because we know the KKT conditions apply, we want to show that x star is the optimal point by the KKT conditions. So for the KKT conditions to apply, we need that the gradient of the Lagrangian in relation to x to be 0. So let's take the gradient and plug in x star, and we would get 0. So this is the Hessian, this is the gradient of the Lagrangian, and we plugged in, instead of x, x star. Why do we know it is 0? Let's go back to what we are given. So the first thing we are given about x star is that this expression is 0, but this is exactly the gradient of the Lagrangian in relation to x. And so we know that this is 0. And therefore, according to the first order optimality condition, x star is the minimizer of Lx lambda. So we know that Lx star lambda is smaller or equal than L of x lambda for every x. We need to show that all the conditions in the KKT conditions apply. So we need to show that the sum over lambda I over the constraint in point x is 0. So this is the Lagrangian in point x star. This is the definition of f, and those are the constraints. And we know that this is 0. Why do we know that this is 0? Again, we can go back to the things we were given. We are given about x star. And we know that for these lambdas, this expression is 0. And those are exactly the constraints multiplied by their Lagrange multipliers. This is one of the conditions of the KKT conditions. So because we know that this is are 0, we know that the value of the Lagrangian at location x star and the lambdas we are given is exactly f of. So we have seen that x star is a feasible solution, and overall we get that f of x star is equal to the Lagrangian at point x star lambda. And as we have shown, this is smaller or equal than the Lagrangian at x lambda for any x, which is smaller or equal than f of x for every x that is in the feasible set. And so, x star is an optimal solution for the constrained optimization problem.